expression, just like any, KQ expression. So, not sure if you remember because this was before spring break, but we learned that KQ is always the concentration of product on top over the concentration of reactants in the bottom. So if we were to write the KQ of the above equilibrium expression or equilibrium equation, it would be Mg2 plus F minus, and remember the coefficients change to an exponent. And then in the bottom, we would have MgF2. We also learned that we don't include solids in the KQ expression because the concentration of a solid cannot vary, it's fixed. Therefore, this can be changed to Mg2 plus times F minus squared. And because this is the equilibrium expression of a solubility equation, we have a special name for it. We call it KSP, which stands for equilibrium constant of the solubility product. But it's the same concept. It's the same thing as KQ, we just have a special name for it, for a solubility equilibrium as such. Okay, so just writing that down, we're using the word KSP instead of KQ. For solubility equilibrium, works just like the KQ expression. Works the same. Still product over reactant. Okay, so I would like you to go ahead and write down the KSP expression of a saturated solution of CaF2. Why did I change that to aluminum sulfide on my notes? There must be a reason. Change this to aluminum sulfide. So F minus is not part of the table, so. When I marked yesterday's quiz that forgot to write the ion charges. Absolutely essential that you write the ion charges because without the charges, it's a neutral atom, which is a completely different thing. Okay, so what does it mean when we have a high KSP value? It means, well, if this number is high, that means these numbers are high. So we have a high concentration of ions, which means that it is relatively high solubility. And when I say high solubility, I don't mean that it is soluble. It's still a low solubility salt, because if it's not, it won't make an equilibrium, right? It's still a low solubility salt in the table, but relatively speaking, it is more soluble than other salts. If it's very low in KSP, that means this number is low, and that means the ion concentrations are also low. And that means out of the low solubility salts, it's considered lower than most things. Okay, so just want to emphasize they are all still low solubility salts. In other words, high solubility doesn't mean it's soluble. And if you look at the 4th page of your data booklet, there's a list of solubility product constants at 25 degrees Celsius of various low solubility salts. And there are ones that are not necessarily on the front page, right? So for example, things like silver iodate. Iodate is not one of the negative ions that show up in this table here, but you know that it's a low solubility salt because it shows up on here with a KSP value. So just take a look at this table, see how, sometimes the KSP can vary from a power of -5 to all the way to like -23 or 39. Iron 3 hydroxide, FeOH3, has a KSP of 2.6 times 10 to the power of -39, which is such a low value. It means even little traces of iron and hydroxide combined will precipitate immediately. And this also explains why certain salts took a little bit longer to become cloudy when you were testing them out in part 1. Okay? So use the solubility product constant at 25 degrees Celsius table when you are doing calculations regarding KSP. KSP, just like KQ, is a constant at 25 degrees Celsius. Even if it doesn't tell you that it's 25 degrees Celsius, you would just have to assume that, because that's the only information that we have with our data booklet. And there are 3 types of KSP calculations that you'll have to deal with. Type 1 is finding the value of KSP when the ion concentration is given to you. Type 2 is doing the opposite, so looking at the KSP value from the table and going backwards to figure out what the concentration of ions are. And then type 3 is predicting the formation of precipitate. So if I were to make a certain concentration of this and this, would a precipitate form? Is the type 3 question. Okay? So pretty straightforward. I think they're easier than the calculations that you've done in Unit 2. But let's take a look at this. So, example, what is the KSP of PbCl2 if the concentration of Pb2 plus is that and the Cl minus concentration is that? All you need to do is find the KSP expression, substitute in the numbers, punch in the calculator, and that's it. Okay? So, write down the equilibrium of PbCl2, that's Pb2 plus, and 2Cl minus. KSP expression will be Pb2 plus times Cl minus. The only way that you can really screw this up is if you forget the coefficients and how they change to an exponent. And I mean, they gave you the ion concentrations right away, so substitute in those numbers. Punch it in the calculator, you're supposed to get 1.1979 times 10 to the power of -5. The numbers are given to you in 2 significant digits, so the final answer will be in 2 sig figs. 1.2 times 10 to the power of -5. And just like KQ, in Chemistry 12, you don't have units for equilibrium constants. So we're going to leave it without any units. Okay, so I think that's the easiest kind of question that you can get, when the concentrations are straight away given to you, as long as you know how to write KSP, easy. With example 2, I tell you that the solubility of a certain salt is 8.8 times 10 to the power of -7. So what do you do here? Just recognize that AgBr will dissolve 1 to 1 to 1. So if this is 8.8 times 10 to the power of -7, this is also 8.8 times 10 to the power of -7. This is 8.8 times 10 to the power of -7. The KSP, which is concentration of Ag plus times Br minus, is simply going to be 8.8 times 10 to the power of -7 squared, because you're multiplying it twice. And this is going to be equal to 7.744 times 10 to the power of -13. Again, the answer should be in 2 sig figs, so 7.7 times 10 to the power of -13. Okay. Sometimes you may have to do a very straightforward polarity calculation before we move on to finding the ion concentrations. I would like you to do example 3. I'll make it easier for you and give you the molar mass of this. It's 99.4 grams per mole. Okay, go ahead and solve this. 1.8 times 10 to the power of negative 2. Here's one confusing concept for a lot of students. And if you don't understand what I'm saying in the next minute, it's fine right now. But hopefully as we do more questions, this will make more sense. Sometimes students get a little bit confused about the difference between example 1 and example 2. In example 1, I gave you the concentration of the salt, and then from there, because this was a one-to-one dissociation, you found the concentration of each ion and then used it towards your KSP. In example 2, you will notice that this number right here, the concentration of Cl minus, is not twice as much as Pb2 plus, even though this is a 1-to-2 dissociation. And then students don't understand why that is. The main difference is that over here, I simply gave you information about the solubility of the salt. So you're just putting this salt in water and then letting it dissociate on its own, which will then dissociate according to the coefficients. Whereas over here, I have specifically given you the concentration of each ion separately. So the way that this can happen is when I have a certain concentration, something like PbNO3 That's a soluble salt that contains lead that has a concentration of 1.1 times 10 to the negative 4, and I'm mixing that with another solution, something like NaCl that has a concentration of 0.33. I'm not necessarily finding, the concentration of this and allowing that to dissociate on its own. If that happened, yes, this will dissociate to 1 to 2. But that's not the situation here. I am mixing two different solutions that contain different concentrations of each ion, and then allowing them to make a precipitate, and then from that figuring out what the KSP of the PbCl2 is. Okay, so I hope you guys see the difference between this condition and this condition. So what I see sometimes is that students, they find, they look at the concentration of Pb2 plus, and then instead of putting this concentration, which was given in the question, instead they just multiply this by 2 because they think it's a 1-to-2 dissociation. But that's not true. This is a different condition. Okay? So I just wanted to, explain that before anybody asks why there's a difference here. Okay? So it all depends on how the question is asked. If I give you the concentration of the ions, use them. If I don't, if I simply give you the concentration of the salt, then you have to assume that they dissociate in water according to the coefficients, and then you have to use those concentrations to find KSP. Alright, here's the second type of questions. This time, the KSP is given to you, and then you have to find the concentration of the ions. Let's do this one. Example 1, what's the concentration of calcium and carbonate ions if the KSP of CaCO3 is that? So CaCO3 will be in equilibrium with Ca2 plus and CO3 2 minus. And I didn't give you the ion concentration, so in this case you have to assume if the concentration of the CaCO3 was X, then this will dissociate naturally according to their coefficients, and this will be X, and this will be X as well. So the KSP expression, which is Ca2 plus and CO3 2 minus, simply the product of those two ions. And the question tells you that this is equal to 4.8 times 10 to the power of negative 9. And if it's not shown to you, then it means that it's going to be in the table. This will be x times x, which is x squared. So to find x, you need to square root 4.8 times 10 to the power of negative 9. It will equal to 6.9 times 10 to the power of negative 5. And since x is the concentration of the ions, you can simply write down the concentration of Ca2 plus, which is going to be equal to the concentration of the carbonate ion, is equal to 6.9 times 10 to the power of negative 5 molars. Okay? Later on, you're going to see questions where I may have given you the concentration of one of an ion. So let's say that I give you a number for this, right? Then you should be able to, because this number is given to you and this number is given to you, like a KSP, you should be able to find calcium 2 plus. Don't assume, let's just say that this was, I don't know, 0.1 molar. Don't assume that this is also going to be 0.1 molar because it's a 1-to-1 ratio. You would have to substitute into the KSP expression 0.1 and then find what Ca2 plus is going to be. Again, this is very similar to what I was saying before, the difference between dissociating naturally and then giving the concentrations of ions specifically. You'll see questions like that in the provincial exam if you've already started working on those. All right, let's try example 2. What is the concentration of the OH minus ion in a saturated solution of MgOH2? Okay. Well, MgOH2 is going to dissociate as Mg2 plus and 2 OH minus ions. If MgOH2 is X, Mg2 plus is going to be X, and OH minus is going to be 2X. KSP expression is Mg2 plus times OH minus squared. From the table, you can see that MgOH2 has a solubility product of 5.6 times 10 to the power of negative 12. So this is from the table. And this will equal to X times 2X squared. I hope you guys remember from exponent rules that the exponent applies to both things inside the bracket. So this is the same as X times 4X squared, which is then equal to 4X cubed. If you don't know how to do a cube root in your calculator, ask a friend or ask me. But please, everyone, check if you are able to get X equal to 1.11868 times 10 to the power of negative 4. Is that the answer? What am I trying to find? OH minus concentration. OH minus concentration, therefore, is 2X, which is 2 times 1.11868. And that is equal to 2.2 times 10 to the power of -4. It is 2 significant digits because KSP is given to you in 2 sig figs. And the concentration should be in molars. We good? Any questions? Okay. Last example. Well, the last example that I'm going to go over with you. What's the molar solubility of Ag2CrO4? What is this question even asking? Molar solubility